got auction and that kind of.
Yeah, that was a fun discovery. Yeah, if you're curious how that worked, I've learned you have to go through here and just type seconds and it just shows that option. Otherwise, it's really well buried. And then Windows 11 complains this might use extra power. So I don't know if that's more for laptops or not. But I don't know. For me, this is a huge quality of life improvement. It's weird not having the seconds. The minutes will sneak up on you. Well, I believe we can begin. Welcome back, everyone. I hope it was a restful holiday for you all. Probably some of us could still be on holiday, but some people might be trickling in right around the minute. Usually, it looks like happens a lot for these classes. So this is week 2 now, and usually week 2 things get a little bit more busy. Homework assignments start coming due. Gets busier for me. Grading starts coming due, and that's a big part of my workflow as well. So probably the best thing to think about week 2 is how does this class fit in with your other class schedules, your home life schedule, your work schedule? The quicker you can get into just a regular routine where you do the studying, do the completing the homework, those kinds of things at a regular time, the easier and easier this class would get, I would say. But any last questions or comments at all, folks, before we get started on today's material? Okay, I don't have a ton of announcements. We are on week 2, and our upcoming exam is going to be on week 4 on a Tuesday. So we'll probably talk about it a little bit more when we are back on Thursday's class. Also, assignment 1 is going to be due next class. And looks like assignment 1.2, this one got pushed to just a week away from today, since this is going to be the week we actually complete it. If we complete section 1.3 today, this due date will be firm. But if we take in a little bit extra time just to complete those topics, we'll move the due date as well. So just a reminder, all assignments just have a 1-week turnaround. And if you're completing your work by the due date, you're considered fully caught up in the class. But welcome back, folks. We left off last class going into our weekend right here. It's kind of hard coming back to a page that's like a wall of text, a whole bunch of things highlighted. But this is a good one to come back to because section 1.2 is all about reduced echelon form and normal echelon form versus a new concept we'll talk about, free variables and the basic variables. So just a quick reminder, quick rundown while we kind of warm up for the class today. This one was the only one considered to be in reduced echelon form because it had 2 pivots, but most importantly, of those 2 pivots, there were zeros below and above and below if that qualified. This one was not in echelon form at all because of the entry right below here where the pivot is circled in orange is non-zero. This one is in just strictly echelon form. I believe I recall putting reduced echelon form by correction from the class. Spotted this entry right here in the red box means just echelon form. It would have been reduced if this part right here qualified. So change that to 0, and now it's reduced echelon form. But one entry off and it would ruin it. And just to emphasize, if there was a 1 right here as well, it's not even echelon form at that moment. We would have had to have a 0 right there. So this one qualifies for echelon form. It would have been reduced if we had a 0 here and zeros here, that's a 9, here and here. Well, wouldn't quite make it reduced echelon form, but it would be close as long as the 2 became a 1 and the 3 became a 1. So that's what we want for reduced echelon form. It makes reduced echelon form sound really super important when we discuss that. But remember, there's roles that these kinds of things take. Let's go back to section 1.1 just briefly to highlight that comment or concept. This is not as new a computer as I thought. Usually open a PDF is a bit quicker. There it goes. So the major concept to be aware of is if we're completely solving the system, if we want the solution set, we need zeros above and below all pivots. In other words, that's just saying we want reduced row echelon form. However, if the question is only about consistent versus inconsistent, is there a solution or not? In other words, we only want the system to have zeros below the pivots. That means we just want echelon form. So we'll come back to that concept as it becomes relevant to these new notes as well. But any last questions at all, folks, with these concepts we ended last week on? Okay, let's get going in earnest then. Next example is a kind of interesting one. They give us a matrix A and they say, reduce it to echelon form. This is kind of an interesting problem because to get full credit on this, say if it came back as an exam question, we are not going for reduced echelon form at all. You'd have to know when to stop, which is again, sometimes an important skill in mathematics. Other interesting things about reduced echelon form is everyone's answer is going to be unique. There is exactly one and only one reduced row echelon form for any matrix you write down. That doesn't qualify for ordinary echelon form. There could be as many correct answers as there are students in the class. In fact, there are infinitely many correct answers. But as long as it's echelon form, in other words, you stopped right at the right moment, you would get full credit. We talk quite a lot about pivot positions, so we'll just mention them as we go along. And I'm going to copy the same kind of highlighting or color coding. As we work through the matrix, I'll circle a pivot position in this color right here as we go to analyze. So another thing that's interesting about example 2 is this is just an ordinary matrix. There's nothing telling us that this was augmented with anything at all. So this one has nothing to do with the system of equations whatsoever. We're just analyzing an ordinary matrix. So first step we'll take is circle this first pivot right here. And on that pivot, our goal is to eliminate entries below. Let's keep using that little shorthand. I won't use that on every section's notes, but if this has been helpful for you to absorb the row operations, then it might not hurt writing this out. What we'll do to eliminate this 2 right here, and I'll try to be careful on my subscripting, is replace row 2 with itself minus 2 times row 1. To eliminate the entry down below, we'll replace row 3 with row 3 minus 2 times row 1 once again. So that means row 1 stays fixed. That's a 1, 2, 4, 5. Kind of interesting numbers on this matrix the more you stare at it. Take, by this first row instruction, negative 2 times row 1, add it to the row below. We'll get 0. Let's go carefully. Negative 4 plus 4 for 0. Negative 8 plus 5 for a negative 3. And negative 10 plus 4 for a negative 6. I need to learn to write a little bit smaller too. Penmanship can sometimes be paramount to organize the work. Then rinse and repeat. This next instruction right here by the red dot says, take negative 4 times row 1, add it to the third row. We'll get 0. Negative 8 plus 5 is another negative 3. Now it's negative 16 plus 4 for a negative 12. Now negative 20 plus 2 for a negative 18. And that's our first row operation. At the moment, I have a pivot here. To find our other pivot, we want to be careful. If I go down 1 and right, you might circle this one, but that's not the right pivot position. We need to reorganize our rows, bringing this one up to make it the next pivot. So that will more correctly reveal the next pivot position, and this is our next operation. If you ever see a 0 right here, but below is a non-zero entry, we need to swap those rows. There's no problem right here with everything at 0, but now what we need to do is take row 2, swap, so bidirectional arrow with row 3. Row 1 is just the same, 1, 2, 4, 5. Now row 3 in first, 0, negative 3, negative 12, negative 18. Some might have divided by negative 3 at the same exact time, and that would have been totally fine. And now row 2 is the new row 3, 0, 0, negative 3, negative 6. Again, if you divide by negative 3, that would have been totally fine as well. And here's the new layout of the pivots. We have a position here, here, and here. So those are all 3 pivot positions. At this stage, would you say we're in echelon form or we need a new step? Anyone see what we should do? It's kind of tricky in a way, right? Because there's a lot of stuff we could do if we really wanted to. We could divide this row by -3, eliminate the entry above. We could do the same here, eliminate 2 entries above. But then if we did all that work, we would have taken it to this form, a reduced echelon form instead. We want to stop at an echelon form. We're not too worried about any extra noise that's inside this, above this, this diagonal section. We don't care if we have different numbers here, just the fact that we have pivots. So we're in a good stopping position. As long as it has this sort of shape where it kind of staircases down, where the pivots are at the top of those stairs, that's the echelon form we're going for. And so this is the stopping point on this matrix here. Kind of tricky in a way because we have to know to stop early when we're used to just reducing things to the fullest. But any questions at all, folks, on that part A? Okay, the instructions are a little funny here. I copied these instructions to be pretty similar to ones you're going to see in the actual homework assignment because those instructions are kind of vague, I thought. It says circle the pivot positions of the reduced matrix. That's this one. This one is it now in reduced to or reduced in echelon form. And we already circled the pivot, so nothing further to do there. It says and the original matrix. So you might circle way up here. Imagine this is your book and this is what we copied down. The pivot positions in the original matrix are here, here, and here. It could have been any 3 columns whatsoever, or maybe there's just 2 pivot positions and it's any 2 columns, or maybe there's just 1 pivot position and it's any one of these 4 columns. But if there were 0 pivot positions, and that can happen, you would have known that already because the whole matrix would have had nothing but zeros. Yeah, go ahead.
Sorry, I just realized you did the math right from the first, you did all the math right, but the R3 becomes R3 minus, that should be 4R1, right?
Oh, it should have been. That's always terrible. Got the
You did all math
subscripts,
above, right?
but not the number. Thanks for spotting that. Let's fix that right away. This is like a permanent record, especially on YouTube. So that's an appreciated correction there. Yeah, it should have been -4 and then added below. Again, another comment on these. These are only valuable if it's not mixing you up, like it seems to be a big struggle for me this semester. Thanks for spotting that. Other questions at the moment?
So if we haven't already like reduced the echelon form, we just assume it's a straight diagonal for the pivot point.
Well, actually, that's one big question about linear algebra. For just looking at these right here, it might have been a straight diagonal. It could have been something like this, for example. Just 2 spots, or maybe 3 like this, so it's a little off-centered. The only thing that reveals where the pivots actually belong to the original matrix is the echelon form. And that's one of the major reasons why echelon form is something we kind of harp at a lot, saying sometimes that answers all of your questions, because a related concept here is that echelon form always reveals locations of all pivots. But when we look at the original matrix, it's not vague where the pivot positions really are until we get it to an echelon form to compare it against. This one, yeah, happened to be just a diagonal starting from this corner, working its way down by coincidence. Other questions at the moment? Okay, part B is weird because we didn't do anything. We were just circling matrices. So let's go up to part C. It says list the pivot columns of the original matrix. And that's important too. Well, these are the pivot columns of the row reduced to echelon form matrix, but the original pivot columns are these 3. So when it says the original matrix, we're doing these, and the answer would be 1, 2, 4. We're going to talk about this notation a little bit more, especially in section 1.3. But we typically in linear algebra would write columns in this vertical format with square braces, much like a matrix, except just 1 column. So second column would be 2, 4, 5. Column 3 would be 4, 5, 4. Any questions about that at the moment? Okay, so this is all about getting something to echelon form. So we know which columns are pivot columns and also which positions were the pivot positions of the original matrix. Really just another way to practice getting into echelon form, studying that concept again. Next things we'll be doing in this section are looking at more about row reduction, finding systems of equations, their solution sets, and again, the concept that we mentioned, the difference between free variables and basic variables coming up. Before we get that, we have our first majorly important theorem in this course. Well, this is more important for chapter 2, and it becomes almost something you take for granted when you're in, say, chapters 3, 4, and 5. Nonetheless, any theorem that's kind of highlighted or emphasized, maybe it has a name as a big giveaway, those are always going to be the important structural kind of theorems that just have massive use. So let's make a bigger deal out of this. This is the first major theorem of chapter 1. Again, it gets used all over the textbook, but it's one of those theorems that you start using kind of as second nature. It gets taken for granted a lot. It tells us everything we would like to know about the major questions in linear algebra for systems of equations. We want to know, is there a solution or not? And once we know there's a solution, we further want to know if that solution is unique or if there are infinitely many solutions. This theorem tells us everything about those questions. So let's work through it carefully. It says a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. So that's probably hard to read. Let's go with blue. So this term determines automatically consistency. So example 3 says, find the general solutions of the given systems. We'll also determine free variables versus basic variables. But already, if you're looking at this matrix here, there's a similar one, the homework. It said, find the general solution to given systems. So we can assume these are augmented matrices. So there's an augmented part right here. This is the right-hand side. And the system is consistent if and only if the rightmost column is not a pivot column, and yet the pivots go here, 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 and here. That tells us this system is done. Anyone know the best answer to give to this one? Would you say it has a solution or no solutions, in other words?
Wouldn't it not have any solutions? Because it has the zeros in the bottom row.
Good call, folks. Yeah, just like you said over Zoom and in class, the rightmost column is a pivot column. So by the text highlighted in blue, not consistent, in other words, inconsistent, or you just may say no solution. Let's just highlight that right there. Rightmost column is a pivot column. So inconsistent. If you said just inconsistent on an exam or homework question, that's perfectly fine. If all you said is no solution, that's fine as well. We're going to consider those synonymous. Yeah, go ahead.
The matrix we ended up with on example 2 at the end, that one would be consistent.
Yeah, if it happened to correspond to a system of equations, meaning the right-hand side was augmented, this is telling you, yes, it's consistent, because the rightmost column here would not have been a pivot column. Absolutely. Other questions at the moment?
So if we replace the 1 with 0,
It would be, yeah. 0 right here, where it's highlighted in blue, forces consistency on this one. Then we'll say a little bit more. There would be infinitely many solutions in that case, because there would be at least one free variable. What do we mean by free variable? We mean something that does not correspond to a pivot column. That's going to happen on this system right here, and I believe the one down below as well when we go to solve them. So first part of theorem 2 is, if you're in echelon form, as this one is right here, kind of a good one to start off, then you can read off everything about consistent versus inconsistent. And if it's inconsistent, nothing further to do. That's what it's mentioning right here when it says, that is, if and only if the echelon form of the augmented matrix has no row of the form like this, where B is non-zero. That happens to be a row 4 on this one in its echelon form. Well, we have a couple more to solve, and I felt like I was about to delete this comment, but I decided not to. All I was trying to say right here, if this looks vague, is sometimes I put a lot of examples on my notes. We don't always solve every single one of them. It's nice to have options, in other words. But I think on these notes, we're going to solve each one of these systems. I have the one written as a set of equations, and 2 where they are augmented matrices provided. We'll work through the theorem 2 on the next couple just to see what's going on. But any last further questions at the moment before we try another? Okay, let's take a look into this system next. This first system, the one we skipped across before doing this one, might as well kind of border this one off. It's a little bit odd looking because there's 3 unknowns in just 2 equations. So when that happens, sometimes you might expect that there's going to be infinitely many solutions. Well, let's see exactly why. Again, when it says find the general solution of the given systems, that means we probably have to go a little bit further in a lot of these examples. Not this one, because it was said we determined it was inconsistent right away. But these instructions right here essentially telling us go to reduced row echelon form until something like a pivot emerges on the far right. That'd be an indication you can just stop at that point. First thing we'll do is go to the augmented matrix on this one. And going column-wise to correspond to the variables, we have 1, -2, then -2, 4, -1, -5, augmented with 4, 6. So we'll row reduce this thing. This one's going to be fast if there's only 2 rows. Our first pivot is in this location. So we want to eliminate that -2, just one operation. Row 2 is replaced with row 2 plus twice row 1. So we go 1, -2, -1. Let me try again on that 1. 4 on our row 1. Then double row 1, add below. We'll get 0. 0 again. -7. And then 14. Our pivots are now column 1. Let me fix that here. Column 1 and column 3. We need to go to reduced row echelon form, and already we can tell this system is consistent. There's no possible way to force a pivot to the very right. You would have to make the -7 a 0 for that to happen, but we never multiply a whole row by 0. That wipes it out, just deletes an equation. That would give us a different solution set. So now, next easiest operation is, let's just divide by -7 into row 2. Quick way of indicating it is just saying row 2, replace with negative row 2, divide by 7. So we get 0, 0, 1, -2, 1, -2, -1, 4. And just about there. It's in echelon form. For every pivot I circled, there are zeros below. This one is just vacuously true. There's no real 0 below that one. It gets to reduce row echelon form the moment we eliminate that -1 right above. So last operation, it looks like. We're going to replace row 1 with row 1 plus row 2. Just strictly add them together. First row 2 is now still 0, 0, 1, -2. And now my border is off. Let's fix that. row one goes 1, -2, and then add these entries up to get 0, +2. And here's where the system ends up. So we want to find the general solution, and we're just about ready to do that. But we're also determining the free variables and basic variables, so let's do a couple things there. First thing we'll do once again is circle the pivot positions. Let's rewrite x1, x2, x3 once again. And it turns out the x1, x3 are what we're meaning when we say the basic variables. The basic variables are the ones that corresponds to pivots. The free variables are the ones that do not correspond to any pivot whatsoever. So in this system, x2 would have been the free variable. Let's write that all out carefully. We have x1, x2 are basic variables. And we'll write next, as we go to solve the system, x2 is free. Let me first hide that system down below. So recall, this is what we did in section 1.1. We just, once we got to our reduced form, we read out what each row is saying. So if we do this again, row 1 by the red dot is saying x1 minus 2x2 equals 2. Row 2 is saying x3 equals -2, but actually let me take one extra organizing step. Sorry for those writing in pen. It's a good idea, and we'll find this really important technique later on, to go in order of the variables. I said something from x1, so down below here I'm going to rewrite x2 is free. Then I'll go back to this row and make a statement for the second row, which is x3 equals -2. So that's a perfectly fine general solution. If you stopped right there, that would have worked out just fine for us. We can go even further and we can say, therefore, the general solution is this. Later on, starting in, say, section 1.4, this becomes a more common way we write this down. We want to solve for the basic variable and write down x1 equals 2x2 plus 2. x2 is free. That's just a statement, but what it's saying is you can allow that to be any number whatsoever, and you have found a solution. x2 can be 0, it can be pi, it can be square root of 2 times 1,000, on and on and on. Free just means no restrictions. It's effectively a parameter. One way you can write that down, and it actually becomes useful later on in these notes, is x2 equals x2. Interesting equation, right? But it's just saying pick anything for x2 and this will bounce here. Once you've made a choice, you substitute it back into the equation above to build out your solution set. Yeah.
Perfect.
Yeah, absolutely. So another question from class is, instead of writing x equals x2, here's another option. Let's write out here as an arrow. Or you can write, I'm a fan of symbols, so I actually like this option as well. It also emphasizes it's a parameter when you write that out. You can write x2 in R. If you like the set theory symbol, you can also express it this way by saying x2 is an element of the set of real numbers. Or you can just literally say in R. It's about the same amount of writing either way. So that'd be a fine way to express the second row as well. Lastly, if you want a solution, there is no freedom at all for x3. It has to be equal to -2 specifically. So that's our general solution. It's kind of like a recipe because you have to make a choice. You have to pick a value for x2, plug it back in, and you'll solve both of these equations as long as you're plugging it to this location as well. Well, notice what's happened so far. We had one free variable, x2 is free. And if we go back to the statements above, you have infinitely many solutions the moment there is at least one free variable. You would have had a unique solution when there are no free variables. In other words, every column would have been a pivot column. So that's kind of the part of what example 3 is all about, determining when do you get infinitely many solutions. One of the columns did not have a pivot, and the system is still consistent. If this one was consistent, like others mentioned, if there was a 0 here, this would have had infinitely many solutions as well, because there's no pivot in column 3 as well. Any questions at the moment, folks, running through this one? Okay, let's try out a couple more. To prevent rapid scrolling up and down, we're going to take screenshots every now and then. So here's our next screenshot. Let's give this next one a try. We'll just cite this theorem as it becomes relevant when we get to the end on this one. Yet another system of equations that we're solving on this one. And it doesn't look like there's so much work to do, but that's kind of nice. We practice a lot of row reduction. This one is all about getting to the major punchlines at the very end. So we have a pivot right here immediately. Move down and right till we hit the next pivot in this location. Down and right, we skip a whole bunch of values until we get to here. And the dotted lines here are just a reminder, it's an augmented matrix. So the right-hand side are the equals to portion. There are 4 variables this time, 5 of them. x1, x2, x3, x4, and x5. And notice how close it is to reduced row echelon form. There's just one problem. So first 2 pivot columns are great. On this pivot column, if that -8 were a 0, our job is done. So here's our row operation. It looks kind of silly, but we're still practicing this. So if you decided to just kind of scribble this out and put in a 0, that would have qualified. Little shortcuts like that on exams and homework is no big deal. But let's write it out for the sake of clarity on the notes. We have to eliminate that -8 for reduced row echelon form. So 1 must be replaced with itself plus 8 times row 3. But notice if you multiply row 3 by 8, there's no change when you hit these zeros. That's the only change. Then you'll take that 8, add it above, and you just put in a 0 here. In other words, if you write all this out, it's loads and loads of copying. So shorthand is sometimes okay if you're doing just a really simple operation like this one. So that's 5 zeros and then 1 more after the augmented, 6 in total. That's row 4, and then it's 4 zeros and a 1. Then a 0 for row 2. 0, 1, 4, -1, 0, 6. And row 1 goes 1, 0, -5, 0. Here's our row operation. 8 times row 3, add to row 1, 0. That's the only change we made, and then a 3. So here's x1, x2, x3, x4, x5. First thing to notice is if we circle the pivots again, it's here, here, and here. There's no pivot in the rightmost column, and so the system is consistent by the statement in blue. No row looks like this, in other words, giving us a pivot in the far right. Other thing to note is we do have free variables. Let me just make sure I match color coding. Basic variables we went with green. So this one, and this one forms a set of basic variables. X3 and X4 are free variables. That means we do not have a unique solution because there is a free variable and you needed just at least one to get infinitely many solutions. So X3, X4 are free. So there are infinitely many solutions. Also, we want the general solution, so let's write this out. This is this point where you might take a bit of a shortcut. It depends on how you're visualizing this matrix, if that shortcut feels nice or a little confusing. Let me scroll up for just a moment to show you what I mean by this shortcut. You'll notice when I wrote out those two rows, I was just writing them down essentially verbatim. And then we took this row 1 and just solved for x1. Some people would rather just jump down to this step right here. If you did that, this is what you're visualizing as row 1. It's x1 minus 5x3 equals 3. Well, let's just solve it for x1 right here. I'd write x1 equals, add 5x3 to both sides. So now it's a positive 5x3 plus 3. Does that make sense to folks as a shortcut? Awesome. So essentially, just imagine this was x1, x2 plus 4x3 minus x4 equals 6. And then just solve this equation for x2 right as it stands. Sometimes this could save you quite a lot of time, especially if the system was a lot bigger. So let's read this out carefully. x2, I'm just going to say, is already equal to, subtract 4x3 from both sides, so minus 4x3. Let me fix that 4. Then it was minus x4, so add x4 to both sides, plus x4, plus 6. Struggling with 4s today. Next, I have a free variable, so I'll just literally write down here, x3 is free. You might have written down x3 equals x3, or you might have used this statement, x3 is an r, and all of those would have been synonymous for the same exact thing. So either option you'd like to go is going to qualify just fine for the solution. Next variable is a statement for x4. x4 is free. Finally, the only way to get a solution to this original system is x5 has to be equal to 0. We did it, folks. That's this whole solution set. It has infinitely many solutions, only because of these parts right here, 2 free variables. Any questions or comments at all? Okay, it's a particular way I wrote this down, kind of really forcing in some organization. The reason for all this is, if you write things down in this kind of way, this is helpful for parametric vector form. Let me say it this way, the format is helpful for parametric vector form in the next sections. We're thinking already sections 1.4, 1.5. We're going to use this kind of format to start writing down solutions in a very particular way. And it seems like we're going to be making mountains out of anthills, but that parametric vector form becomes excruciatingly pivotal when we get into, say, chapter 4, when we're describing null spaces, column spaces. That just seems like a parlor trick, but then that's all about chapter 5, eigenvalues and eigenvectors. So all this kind of stuff in chapter 1, when you're in the last part of the semester, you might want to refer back to chapter 1, because these are all like the main techniques you're going to be seeing over and over again in some of the later chapters. So if it looks like I'm writing stuff down kind of weird, usually it has a purpose. We're gunning for a particular way of writing things down. Say, this is already useful for eigenvalues, eigenvectors, way out in chapter 5, which is surprising. Well, this is pretty much the major things we're doing in this section. Kind of like a redo of section 1.1, just more vocabulary, a little bit more notation, and that extra big theorem. And just like the last notes had a more abstract one, we have another more abstract one, example 4, we'll take a look at next. Any last questions or comments before we go to finish off these notes? Okay, let's take a look into this last one on example 4. Deserves a whole new page. The whole purpose to example 4 is that theorem again. Just taking a look at the content of this theorem, seeing what's really saying in view of a totally new system, but now with 2 unknown values, parameters in the system. H and K. So we want to determine the values of H and K such that the system has no solution, a unique solution, or infinitely many solutions. In other words, it never said find the general solution. It never said solve the system. So all we need this time is just echelon form is needed. If you're being asked about the nature of solutions, whether they exist or not, how many, this will do the job for us. It's a really fast system, so if you took one extra step, no big deal. But these kind of things are pretty helpful down the line when systems get a little bit bigger. First thing we'll do is, just as normal, let's transfer the system of equations into an augmented matrix. Column 1 is 1, 2. Column 2 is -3h. And now it's augmented with right-hand sides 1k for column 3. And because we just need echelon form, this should be just a one-step operation, kind of relaxing in a way, just to do one step now. We have identified a pivot here, so we need to eliminate entry below. That just means row 2 is replaced with row 2 minus 2 times row 1. I think that's deja vu. We've taken -2 times row 1 a lot. So multiply row 1 by -2, add to the entry below. First, let me write in my row 1. And we get 0. This is going to be +6 plus h. And then this will be k minus 2. Does that look all right to folks so far? Okay, I'll not circle the pivots this time. We definitely have a pivot right here on that entry, but whether there's a pivot here where the red dot sits, I mean, that just depends on h now, right? If h is -6, it's a non-pivot. So I'll avoid circling that because it might be kind of a confusing miscommunication. So we want to determine what happens for h and k so that there's no solution, unique solution, or infinitely many solutions. So now it's all about h and k. What's happening on those two portions of the system? Let's work at this really carefully. So for part 1, no solution. Anyone see what would have to occur for h and k to force no solutions whatsoever on the system? I'll go first. If you want no solutions on this, first thing you need to eliminate is that pivot position. And you can make that happen if h is -6. No possibility of there ever being a pivot there. It's now 0 in that location. Anyone see what we must say about k now? Exactly. The moment, as you said, k is not equal to 2, we've forced a pivot into column 3, and that means it's now contrary to the statement highlighted in blue. It was consistent if column 3 is not a pivot column, but once you said k not equals -2, the rightmost column is a pivot column, it's become inconsistent. Again, that's just synonymous with saying no solution. So that's the name of the game. This is honestly pretty confusing in a certain sense. You'll see a problem like this again in the homework, and this is often a pretty good candidate for an exam question as well. There's not a lot of computation, but it forces us to really think about this theorem carefully. So let's try this again. This is a trichotomy, like we mentioned in the 1.1 notes. These are the only 3 things that can happen. And now we didn't focus about this as much on these notes. Let's go for unique solution. Any volunteers to say what has to happen to get a unique solution?
H is not equal to -6 and k is not equal to -2.
Absolutely. Really, there's no restriction on k, however, but the first part you said is absolutely dead on. H not equal to -6. The reason that's perfect is now you have a pivot here, you have a pivot here, and that's all you need for a unique solution. There are no free variables whatsoever, in other words, and this is what gives us that unique solution. X1 is a basic variable, corresponds to a pivot. X2 is a basic variable now, corresponding to the next pivot. And reason no restriction on K is it could in fact be a 0 in this case. It's allowed to be any real number whatsoever. So let's say it here this way. K is any real number. Or you might have said K is free. That might be kind of confusing because we usually reserve that for X1, X2. But does that make sense to folks on that one there? Awesome. Really, we're just going through what's essentially 3 parts of this theorem. Portion highlighted in blue tells us when it's inconsistent. Here, we forced a pivot into column 3. Then this part right here tells us if you want a unique solution, just make sure you have a pivot in column 1, column 2. And if you want infinitely many solutions, well, you just need one free variable. How do we get a free variable? Let's write this out. Infinitely many solutions means free variable has to be in the system. Can't be X1. X1 is going to correspond to a pivot no matter what. There's no parameter here to adjust. So this one, we can force that to be a free variable. We just make H equal -6. But now we have to be cautious, right? If H is -6, that's how we got to no solution. We have to say something about K as well. Anyone see how to force this to be consistent? What should K be in this case? Or what should we say about K?
Would we have to make K equal 2 so that it's 0 on that bottom?
Yeah, exactly. If you force K equals 2, as you said, now you don't have something like a contradiction, 0 equals 5 or anything like that causing us problems. You just have 0 equals 0, and that's a perfectly fine statement, doesn't bother anyone. And now there's a free variable because no pivot here when H is -6. That's what gives us the infinitely many solutions. We just have to force in a free variable in that kind of way. That means we did it, folks. That's the rundown of this theorem 2. It answers the question in section 1.1 of how do you determine no solution, a unique solution, infinitely many solutions. And really the use of this theorem will be for us, parts 1 and 2, look at where the pivots are. And if it ever is in the farthest right column, we'll just know there's no solution to the system outright. Well, any last questions, folks, getting through these notes for that theorem 2? So no solution. Yeah, right here should have been not equal to. And for infinitely many, we would want H is -6 for a 0, K is equal to +2 for a 0 as well.
So I think it is -2.
Oh, I've got you. I see what you're saying. So K not equal to a +2. Yeah, bad arithmetic on that one. That took me a minute to even see that mistake. Thanks for pointing that out. That should have been K is not equal to +2. Bad algebra on my part right there. That should have been an easier equation to solve. You know what? Let's leave that arrow stay there just for the extra clarity. Other questions at the moment with this one? Okay, well, we did it, folks. That's 2 sections down. Sections 1.1, 1.2, you could think of it as kind of one big section, like we mentioned before. When we go to section 1.3, that's where we start to see more interesting ideas being thrown at us. Section 1.3 is the so-called vector equations. Which sounds new and exciting. We're going to be talking about vector arithmetic, vector spaces loosely. But really the big takeaway for this whole section 1.3 is 2 critical definitions, not necessarily about the theorems this time. One critical definition is the so-called linear combination. So this is something that's going to come up critically over and over again. But linear combination is kind of contained into the biggest definition, often one of the most confusing definitions in the entire linear algebra course, spanning. So everything that we do that involves chapters 4, 5, and 6 involves lots of information about spanning. And this section is our role of getting started on this. We mentioned before, linear algebra is kind of different. There's lots of terminology, lots of vocabulary to master. But if you'd like to see how things are structured, here's the overall goal with all this content. We're going to define linear combination for the first time. And spanning is just the set of all linear combinations. When we combine this with linear independence, last part of chapter 1, we're going to get something called a basis for a vector space in chapter 4. And our major goal is to say, what is the dimension of a vector space? For just a quick example, if you imagine this as the R2 plane, we would consider this to be a two-dimensional vector space. Ordinary space-time, the space component would be 3 dimensions plus 1 time component, so a 4-dimensional vector space. But vector spaces can also be really abstract, so there's a lot more to say to this kind of stuff. And so in these notes, here's where we start working through the definition tree. And spanning, again, seems to be kind of this most slipperiest concept among all of them. So we'll take our time with these notes, make sure we have a really good understanding from a definition point of view. I have a couple ways to visualize this. From a computational point of view, generating vectors in a span, and even a geometric point of view. We'll look at stuff in R2. The reading gives really nice graphics for R3 to help me out. I'm not a great artist for that kind of stuff. And so here's where we start again throwing in more definitions, start talking about a vector space. That's also why we've been writing down a lot of things in column form, particularly in section 1.1 and a little bit in section 1.2. So these notes start off kind of light though. It's more of a get everyone on the same page when we're just starting off with this content. Especially if you take in, say, Calculus 3, you're probably already describing your vectors a little bit differently through initial vector brackets, say like this. A vector written this way could also be considered in column form, a vector in this way, 1, 3. It's kind of annoying to have two different algebraic systems for representing the same thing, a vector. This is useful for linear algebra because of the vector arithmetic, and even more importantly in chapter 2, matrix and vector arithmetic, the actual structure of how you multiply things through. It's very helpful to write things in certain ways. So column vectors take a really dominant role in linear algebra. So column vectors, again, look like these. It just tells you where your first entry is, your second entry. It can also be indicated abstractly, where W1, W2 can represent any real number. If we take the set of all vectors with n entries, we refer to that as Rn. In other words, R2 is a set of vectors of the form W1, W2, such that W1 and W2 are in R. Kind of a weird way to write things, right? When we say R, we just mean the set of all real numbers. So the real number line, essentially. R2 is now telling us we have a structure where there's a first component and a second component. R2 you can visualize as a plane, as we've done a couple times, or as a set in this kind of way, where the colon right here is just read as such that. If we're talking about R3, there would just be 3 entries like the ones down below here. So these are vectors in R3. And if we need to be kind of generic, say we're writing down a definition, if n is unspecified, we'll just talk about Rn. N could be 4, because it uses R4 a lot, or it could be 30 for doing something application-wise and so on. One thing that's kind of interesting in linear algebra as well is we've already talked about some matters of notation, and the zero vector is always one of those really special vectors that you could write down, and depending on the context of how it's been written, it could be really confusing of what you mean. So if I just say zero vector and I have something typed out, it might be written this way. It's usually going to be bold to indicate it's a 0, as a vector, not as a scalar. If I'm writing it down as a notes or using the pen, I might write down a zero vector like this, with a little hook above it to indicate I'm not talking about a scalar anymore. I'm talking about the number 0. I'm not good at writing in bold to really indicate I mean something like this. So that could be written as 0, 0, 0 in R3, for example, or zero vector, we might be working at R2, would be written out explicitly as 0, 0 in R2. And the context has to make this precise. If I can't say if we're in R2 or R3, and I really need to tell you which zero vector I mean, I might have to write down the zeros just like this to make that concrete. Well, that's the zero vector so far. The next object we want to talk about, just to get everyone on the same page, is vector equality. This one isn't too bad. This is the same as matrix equality we'll see in the next chapter. We'll say two vectors, or later on two matrices, are equal if and only if their corresponding entries are equal. So looking at example 1, if you're like me, they look pretty equal, except entries 1 and 1 match, but entries 2 and 2 are different, and entries 3 here, different as well. So we would say these are unequal, just due to different corresponding entries in rows 2 and rows 3 of both vectors. That's a quick rundown of what's going on in the notation. Some symbols we'll see a lot, like R2, Rn, zero vector, and vector equality. Any questions so far, folks, about what's going on here on page 1? Okay, next, after we go beyond page 1, we're getting into ideas of what we mean by a vector space. A vector space is a set like R2, or it could be more abstract, a set of polynomial functions, for example. Even more abstract, a set of functions like cosine functions, bunch of trig functions, hyperbolic functions, and so on. What you need is a set, something concrete or something more abstract, and a set of operations. And the operations we deal with in linear algebra are vector addition, scalar multiplication. Doesn't matter how bizarre your set looks, as long as we can define those two operations, this forms a vector space. So vector addition and scalar multiplication forms a so-called vector space. There's a lot more to say about that. We have more issues that we'll look into in chapter 4. So the full definition of the vector space, if you're really curious, take a look in chapter 4. There's a long list of axioms that your set and two operations have to satisfy. But for the moment, this is a great analogy. Let's work in R3 to talk about what do we mean by vector addition. It means you have two vectors, the same exact entries, so 3, to form out vectors in R3. To do vector addition, you do kind of the nicest operation possible. Add corresponding entries. So entry 1, U1, from the first vector U, and entry 1, V1, from the first vector V, form entry 1 of the sum, U plus V, and so on down the line. So that's our vector addition. And you might know a lot of interesting geometric properties about vector addition, so-called parallelogram law and other interesting things. We're going to focus more on the algebraic side, but there are interesting graphics you might take a look at in the reading as well. So aside from vector addition, we also have scalar multiplication. So when we say scalar, again, we just mean an ordinary real number. So a scalar, sometimes our author calls these things weights rather than a scalar, which is synonymous. Just means some number in R, any real number. It could be 0, it could be 12, and so on. When we say take scalar multiplication, it just means take your vector U and multiply across every single entry by your scalar C. So that's what it would look like. And again, I guess I didn't need to write that out. I forgot I wrote it down here. Take those two operations together, Allow certain axioms to hold. These are some of those axioms here we'll take for granted. And you have a vector space. So our first example too is just working with this, but it also defines linear combination. So it's kind of a preview example. But any questions with our two fundamental operations? Okay, kind of a weird chapter, right? Or section of the chapter. Feels like we were talking about one thing in section 1.1, 1.2, something totally different in section 1.3, but they all go together. So we're just looking at more algebraic properties exclusively at the moment. Now, the next thing we're talking about is linear combination. Again, this is part of a really tricky set of definitions. We'll later on say the span of a set of vectors is the set of all of its possible linear combinations. So understanding that tricky definition span is all about knowing what a linear combination is in the first place. I have it here in bold, even though we haven't defined it. Sometimes it's best to define things first through an example. So I have two vectors. These came out of R3. A linear combination is anything that looks like this. It could have been 0u plus v. That just gives us v. Or it can be 10u plus 12v. Any combination where you change out the scalar 3 and the scalar -2 here for any real number whatsoever gives you a linear combination. So this says, compute the linear combination showing all steps. Kind of relaxing algebra, so it means it's an easy opportunity to make a mistake by going too fast. So let's do it carefully. Here you'd just kind of follow your nose with order of operations. 3u is an ordinary multiplication, but it's a kind of multiplication. It still has precedence over the scalar or vector addition. So first thing we'll do is go to the vector u, rescale by 3. That just means triple all entries. 0, -3, 15. I put a plus here just for my own sanity so I don't get mixed up on negative signs. I'm going to scale this by -2. You could have scaled it by +2, just maintain your negative sign, and that would work out just fine. I feel like I'm more accurate when I scale by -2, just takes that negative out of there once and for all. So I have 6, -4, -14. And that's the scalar multiplication side. Then we just do the vector addition. From the notes above, vector addition is just done row-wise. So in row 1, add those entries, and so on. Row 2 is -3 minus 4 for a -7, and row 3 is 15 minus 14 for a +1. So 6, -7, 1 is a linear combination of u and v using the specific weights 3, -2. So there's lots of different ways to say this, but the idea of what linear combination looks like is really the major goal of example 2. Kind of like example 1, these are more warm-up questions more than anything. But any comments at the moment, getting through either one of these? Okay, we kind of glommed through the algebraic properties, but these are just the kind of things that you would take for granted in the ordinary real number line. This just says it extends to the real numbers. For example, this is often called the commutativity law. This is associativity law. Here, that 0 is tricky. This is context sensitive. Better written bold u because that's a vector. So if you add a 0 vector to any other vector, you result in that same vector. And it doesn't matter if you post added or pre-added that 0 vector, and so on. So essentially, this list of properties is telling you the algebra you take for granted in the real number system carries over in the reasonable way to vector addition, scalar multiplication. So let's take a look at some of the new ideas. Here's where it gets a little bit tricky because we're mainly dealing with sum notation. And these two often do come back as typical exam problems. They're useful because we have a lot of ways now to write down a system of equations. We can write down just the ordinary equations themselves. We can write down an augmented matrix. And oftentimes, a vector equation is a handy way to write down our system of equations. This becomes almost mandatory in chapter 4 when our vector space isn't like R2. Maybe it's a set of polynomials, and we have to write things in a specific way. So this is more of a translation kind of example. If we are defining vectors and we have vector addition, scalar multiplication, we can also write down a system of equations in this way. This is the vector equation down below. It says write a system of equations that's equivalent to this vector equation. So it's like we want a system like in day one in section 1.1 that this now represents. You could do this with no steps whatsoever. But I think it's kind of fun and educative to actually use scalar multiplication and vector addition and vector equality just to see how it all comes together. So shortcut is encouraged if you know exactly what to do, but this is the process. Very first thing I would do is scalar multiplication. When we do the scalar multiplication, x1 here, the unknown, is the scalar, and this entire vector becomes 3x1 minus 2x1 plus, and then rinse and repeat. Vector 2, 7, 3 gets rescaled by x3, so it's 7x2, 3x2. Next one down the line, this is negative 2x3. X3 equals the zero vector, this time written as just 0, 0 in its ordinary column form. So this is still a vector equation just like before. We have a sum of vectors on the left, so we can simplify this in a certain sense by doing the vector addition step. The vector addition step says if all the vectors are the same size, add the corresponding entries. So this becomes 3x1 plus 7x2 minus 2x3. So that's first entry. Second entry is negative 2x1 plus 3x2 plus x3. And this is set equal to 0, 0. So we're just about there. Next thing we do is vector equality. Much like the very first example on these notes, we said two vectors are equal if and only if their corresponding entries are equal. And we're asserting vector equality right here. So by default, that means entry ones are equal. 3x1 plus 7x2 minus 2x3 equals 0. Notice you could have read that off just right here. You would have just paired 3 with x1, 7 with x2, negative 2 with x3, and this is the result you would get. That's their shorthand, and you're welcome to take that. It's good to see this at least once because we're going to also do this kind of thing with a matrix equation down the line. And it does sometimes get kind of notationally jarring to see these different ways to write things down. Finally, entry 2 says negative 2x1 plus 3x2 plus x3 equals 0. And this is our system of equations down below. One word of warning, this gets confusing on a real exam 1 if it's asked a question. When it says write a system of equations, we mean not an augmented matrix. This is like the number one easy to make mistake for this kind of question. Well, any questions at all, folks, doing that kind of translation between the original system and the vector equation? Okay, we'll go backwards on the next one, and we'll also take a shortcut just to emphasize what that would look like. But I also want to emphasize there's something special about this equation. Right-hand side are all zeros. That's an entire section in chapter 1, right in the middle. System of homogeneous equations or homogeneous equations. Let's write this out. This is a homogeneous system due to only zeros on the right hand side. That seems like such a small comment, but homogeneous system of equations turn out to be super, super important in this kind of way. That's what linear independence is all about. How many pivots do you have in a homogeneous system of equations? There's a free variable, you'll say you have dependent vectors, linearly dependent. If there are no free variables, you'll say your vectors are linearly independent. That together is one of the key ingredients for a basis. So we're really looking at both spanning and linear independence all at the same time on these notes. A lot to talk about, so we're not going to rush through the next portions. It looks like the next problem, let me take a peek. We'll look at the definition, and I think example 4 is probably a good stopping point. I don't want to rush through the row operations on the very next system. But these are really good notes to come back to because this is where a whole big tree diagram of stacked definitions, almost like a house of cards, really begins. Understanding homogeneous systems really well in the next sections, and critically understanding how spanning goes is going to affect your entire course in linear algebra. Everything, well, not everything, but so much comes back to those concepts. But let's try this out again. This one started out as a system of equations. This time it's 3 equations and 3 unknowns. What we want to do is write down the vector equation that could represent this. The right-hand side is 3, 1, 2, so this is not a homogeneous system like the one above. And in view of the shortcut we took with the last problem, all these steps are reversible. You could take this, write it down as a matrix equation, but this feels like directly copying it in, right? You're just putting brackets around certain sides. So this is what step 1 would really look like. You bracket it out in this way, then you would undo the vector addition to get to here, then you would undo the scalar multiplication to get back to here. Let's do it in one fell swoop. You're welcome to do this in the homework as well. The way I'd write this out is start with x1, which is now a scalar. It's going to multiply the constant vector, pull coefficients, 3, negative 2, 5. It's as if you're building an augmented matrix, except you're putting down the column all on its own and putting the scalar, the unknown, right in front of it. Then go plus x2, pull coefficients again. X2 coefficients are negative 2, negative 7, 4. Plus, once more, x3. Coefficients are 4, 5, 3. Oh, good call. Negative 3 on that one. I totally just read it over. And to make it a bona fide equation, this is sometimes honestly easy to miss. You do have to have an equals to somewhere in there. And this is where we would have put a dashed line if we were doing an augmented matrix. But again, this is asking for something specific. The vector equation. So 3, 1, 2 in that formatting has to be written in this way. And we did it, folks. Again, examples 3 and 4 is just translating between different kinds of notations to say the same exact thing. This was a system of equations, and this is an equally same way to represent that system. Both would have the same exact solution set. All we're doing is focusing more on the very columns themselves. We can tell something about those columns, what they span, if they're linearly dependent to linearly dependent. It tells us something about the nature of those solutions. So that's part of the reason for doing all this kind of work. Well, when we come back, we're going to delve into linear combination more formally, answer questions if a vector B is a linear combination of some vectors, these 3 in particular, and that segues us into learning about spanning, the big part of these notes. But any last questions at all, folks, before we call it a day? Okay, well, welcome back from the holiday. Have a great afternoon, folks. If questions do come up at any point, don't hesitate to reach out. I'll be happy to help. We'll return right back here in the next class, and we'll probably also have the 1.4 notes to make it really start with as well. But take care. I'll see you all on Thursday.